Okay, now that we know about magnetic fields of moving charges, let me just focus here on the size. We have mu naught over 4 pi q v cross r hat over r squared. Sorry, I guess I got the whole thing there. Okay, now we can get magnetic fields for single particles that are moving, single charges, but most often our magnetic fields are created from currents. So lots of charges moving in a wire. And our goal is to be able to use this knowing that current is just a bunch of charges moving. So I is equal to dq over dt. A bunch of charges moving in time. That's what I is. And so we're going to try and get this to look like that. So if I write this and say dB is this little dq that's moving, okay, and consider it as part of a wire. So here's a wire. Let's say current is flowing this way, and so there's a little piece of it. This is dq. It's of length ds. And I'm trying to find the magnetic field from that piece at some point. Let's just say like right here. So the r would be like that. Now its velocity would be in the direction of the current. And so I want to try and get this to be expressed in terms of this current, which is something I can measure. I could hook a battery to this wire, and I can actually create current. I can measure that. So how can I recast this? Instead of thinking about single charges moving, think about the whole effect of all the charges in this wire. So to look at that, I can say that dB is equal to the constants, and dq times, what is velocity? Well, velocity is just ds over dt. Okay, that's all it is. The velocity is distance over time, so it's a ds is charge moves that length in time. Okay, divided by an r squared. Well, when we get small enough, this is just a number, that's just a number, and that's just a number. So I can switch this fraction and move this dt underneath the dq instead. I get mu naught over 4 pi dq dt ds cross r hat over r squared. But what is dq dt? That is our current. Mu naught over 4 pi I ds cross r hat over r squared. And so now I can say, well, the field, the magnetic field here due to this piece is equal to the current, which I can measure, times the length of that piece. Then cross r hat and so on and everything else we've done. Now note that this is just dB. To find the B field there, I'm going to have to do it for all pieces because there's another piece of charge right here that's moving, and it's got an r hat, and it's creating a magnetic field there. And so guess what? To find B, I would have to integrate this. Being careful that it's vector nature, are they adding, what components are adding, doing all that. Okay, now we've done similar mathematics for continuous charge distributions where there's just a charged rod, but here we're doing charges that are moving, and they have a different effect because of this cross product. Okay, and so I'm going to leave some of those derivations for the text. The mathematics is what's interesting there, and we've already done that. Okay, but what's most important is the end results. If you go ahead and integrate this for a really, really long wire, compared to the distance away from that wire, a really long wire, you end up with mu naught I over 2 pi r. Okay, where r is the perpendicular distance from the wire. Okay, so it doesn't matter when you have this wire. It doesn't matter if you're there or there or there. We're assuming this wire is so long compared to this, and we're far enough away from the edges that this can be true. Okay, that's a really powerful one. We can use that a lot. We could also instead have a bent wire, a loop of wire. Okay, and we can calculate, do this, integrate this for a loop of wire, and we get B loop is going to be equal to mu naught over 2 I r squared over z squared plus r squared 3 halves. And so this is a geometry where we have a loop, and Z is measured perpendicular to the loop along the axis of the loop. So along the symmetry axis of the loop. And R is the radius of the loop. Current's flowing in the loop, so we're measuring far away from there. Now, a very common one that's super valuable is what about when Z is 0? If you just plug Z equals 0 in here, then you get I R squared over R cubed, which just leaves an R below, and you get mu naught I over 2R. And that's a super convenient result. Now, do be careful that the long straight wire looks pretty darn close, except there's a factor of pi in it. Okay? But this one does not. Okay, another one that's really valuable is the solenoid. The solenoid is basically a bunch of loops stacked on top of each other. Okay, and I'll show the result and then I'll draw the picture. But a solenoid has mu naught Ni over L, where N is the number of loops and L is how long. So this would be a picture like this. We have basically a wire comes in and it's looping a whole bunch. Okay, and this is the length L. That's length L, and there are N loops in it. Okay. Now, sometimes we don't know how many loops there are and how long the whole thing is, but we do know the number of loops per unit length. And so sometimes we'll group that N over L together to create just an N, a little n, which just is the number of loops divided by L, or a standard density of loops, you might say. So that's a solenoid. Now this one is the most powerful. You're gonna see that this is to magnetic fields as capacitors are to electric fields. So this one we need to pay a lot of attention to figure out how it works. And we're going to go into that in more detail. But the important thing I want to point out now is that this is the field inside those loops. Outside the loops, it is 0. There is no magnetic field outside the loops. And look at this. There's no distance dependence. I don't see any R's, any Z's here. This is just a number. Mu naught's a number, the length is a number, I's a number, N's a number. So it doesn't matter where you are inside this, it's constant. And because it's constant, we can do powerful things with it. So remember that the solenoid is super important. Now these are all derived in the text. I'm going to leave those derivations for the text. We're going to focus on using these. Now one that's kind of cool, I do want to point out, is a dipole. Now so many medical imaging rely on the fact that our atoms in our body they're basically small current loops. They're little loops where a single charge is flying around the nucleus. And even more than that, single like protons can have a magnetic moment. And basically they can interact with magnetic fields. And so we can take this loop idea and say, well, no, I can't really measure the current. I can't really measure the radius of the loop, but I can measure how it responds to magnetic fields. And so we can do this to find something. If I just multiply the bottom by pi r, okay, by 2 pi, multiply the bottom by 2 pi, so it was 2, now it's 4 pi, which means I have to multiply the top up here by 2 pi. Okay. By doing that, I end up with 4 pi here, mu naught over 4 pi. And this r squared times 2 pi, if I rewrite that and say 2 pi r squared, I apologize, not 2. I don't want a factor of 2 down here. I just want the 1 factor, or just the pi. I apologize. I messed up on that. The pi times r squared, well, that's just an area. That's just an area of this loop. And so I can say, oh, well, this is just I times an area. And then I can group all that together and call it something different. We'd have mu naught over 2. And this is just called the magnetic dipole moment, which would give the variable mu. No mu naught, just mu. And then we're going to, we could put it over this denominator here, but I'm going to take the fact for a molecule, R is teeny. This is super small. And I could measure this from, millimeters away. So Z is huge compared to R. So I can get rid of this, and I end up with just a Z cubed. Okay? So with mu being defined as IA, this is the magnetic field, what we call a magnetic dipole. If you remember the electric dipole that we calculated for electric fields, this is the magnetic dipole. And this is applicable in lots and lots of problems, and especially in biology, because every atom, every proton actually, can have a magnetic moment. This is the magnetic dipole moment, and interacts with different things, so we can image the body in a variety of powerful ways.